Bismillahirrahmanirrahim. Hello everyone and welcome to my presentation. My name is Alla Adel. I am PhD student at Lakwat University in Department of Science. As you can see on the screen, our topic today is potassium lithium sulfide as a new p-type transparent conducting materials by first principle study. My presentation is divided into 4 parts. I will start with introduction, then I will move to talk about the computational method. Next, I will focus on the obtained results, ending with conclusion. Let me first explain what transparent conducting materials are, which are commonly abbreviated as TCM materials. The first part is exactly what you think it means. A materials transparent to the visible light, like a glass window, and I am sure that you have a couple of these at your home. And typically material with these properties have a large band gap greater than 3.1. Secondly is conducting to the electrons, for example the copper, gold and silver. Once these two properties present in one material, will be enabled to a lot of applications. Actually, TCM materials, we encounter them every day in our life, but it's hard to notice that since they are transparent. These materials typically used in all touch-screen based devices like smartphones, tablets, also in solar cells, light-emitting diode, and others. The most commonly known TCM are indium oxide, zinc oxide, tin oxide, and gallium oxide. As you can see, most of them are oxide and N-type, although some oxides have been suggested as a P-type TCO. Their materials properties stay poor and lower performance, especially the carrier mobility, compared to the N-type. However, finding a P-type TCM with wide and high transparency and high mobility would lead to a significant advances and wide range of technologies. This makes the development of a novel P-type TCM a very challenging field. Potential material for P-type TCM should offer a high optical transparency, which means a wide band gap greater than 3.1 electron volt, and 2, a high Hall mobility, which means a low Hall effective mass. Let me briefly summarize the computational method. This work has been done within the framework of density functional theory, DFT, which is one of the most powerful and successful computational methods. However, in definition, DFT is a computational quantum mechanical modeling method used to investigate the electronic structure of atoms, molecules, and solids by solving the many-body Schrödinger equation. All the results reported here were calculated using Vienna Abination simulation package, VASP, which implements the pseudo-potential plane wave method within the density functional theory. Also, we have used the projector augmented wave as a pseudo-potential, where GGA and HSE have been used to treat the exchange correlation effects. Okay, let's now move on to the results. This figure summarizes the crystal structure of the considered material. As you can see, potassium lithium sulfide formed by alternative layers of potassium and lithium, and each layer of potassium or lithium surrounded by 6 atoms of sulfide. Our obtained result lattice parameters are presented in table 1, and we can clearly see that our results are in good agreement with the experimental data, which is a good start point for this work and very important. In order to find out the band gap and the effective mass of the studied material, we have calculated its band structure So based on this figure, we can conclude that this material is a semiconductor with indirect and direct band gap of 3.37 and 4.31 electron volt respectively. If we look at the table, we will see that our results are very closer to the experimental, much better than the other theoretical available in the literature. However, this material has heavy and light Hall effective masses. The light effective masses is equal to 0.22, which is a competitive with the industry standard and type TCM, while the heavy Hall effective mass is equal to 0.84. In fact, this value is superior to the sum of the top performing P-type TCM materials. Now I would like to turn to other important properties which can give information about transparency, the optical properties. As the figure shows, our studied materials has no absorption for the entire visible region, and its reflectivity is less than 20%, indicating the high transparency of the visible light for the studied material. Conclusion: potassium sulfide has even large band gap, small Hall effective mass, and low reflectivity for the visible light. However, this material is a promising candidate for the P-type transparent materials, TCM. And thank you for your attention.